So for those of you who took yesterday's seminar, you have a stronger point of view, a stronger understanding of the metrics per se. But yesterday's seminar also talked about from a supply chain balance, yesterday's seminar also we discussed about the importance of a balanced value chain and how metrics could be used, to basically create that balance and create a holistic value chain that aids performance, that really helps improve the efficiency and effectiveness. So yesterday we covered a lot more than a narrow focus of, the mechanics of demand metrics. So today we talk about demand metrics, and our single objective is to improve the quality of the forecast models. So, if you are not using APO, and I assume most of you are using SAP, SEM, or APO, so if any one of you is not using APO, you can kind of like understand the overall theme of the seminar from a modeling perspective about how do you use metrics and how do you use them specifically as a diagnostic tool to improve the quality of the model. So it's really, even model building is an iterative process, right? You build a model and you look at the error or the model error, right? It's not the forecast error yet because it's all based on the past. And what do you do with it, and how can you interpret the diagnostics that you get, and how can you improve the forecast models? Now, the interesting thing is APO is a very powerful tool. We have a variety of models in SAP APO, SCM tool. And these models can be put to good use in improving the forecast accuracy of any organization. Now, one thing that I have noticed or I have observed in consulting with, a number of clients in this space, SAP clients who have implemented APO, either implemented it, 3, 4, 5 years ago or just recently implemented, what have you. One thing I have noticed is, the models are not effectively used by the planners. I think either because of a shortcoming in training, or it's because, I think sometimes it's also the implementation configuration per se, right? There could be shortcomings there. So, some of the things that we observed in some clients is really the configuration, I think as with any big project, there is a lot of stuff that goes into planning. There is a lot of stuff, and a lot of time is spent probably by the consultants on the data mapping and product hierarchy and all this other stuff, master data and all that other stuff. When it comes to the key area, which I call as the sweet spot, they are either squeezed for time, or the consultants themselves don't really have the knowledge to map the business process and the business challenges back into what the tool can do, right? So anyway, it's not a criticism of consultants. I know we have some very good consultants here also attending the session today. But, the outcome per se for the user is that, they end up with a tool that looks good, but, either they don't know how to leverage it, or it has some challenges that have to be overcome before it can be used. So what we have done over the last 3 years is we launched what is called as usability consulting, not just APO DP, but also Our expertise is specifically the supply chain area, specifically demand planning and inventory management. We don't really do anything else. We don't do warehousing, transportation, logistics, distribution. We don't do any of those. We just specialize just in demand planning and inventory planning. So basically, what we have done is with the launch of this usability consulting, we work with clients who have implemented either APO, or Oracle Demantra, Managistics, the JDA tool, what have you, is to really try to kind of bring the business perspective and try to analyze the business model and bring back what the business requires and how we can marry up the business requirements with the power of the tool, with the modeling engine. So, this has been variously called by various clients. Clients will call it model tuning consulting, exception management consulting. We really call it usability consulting. So the objective is to improve the usability of the software. You may have seen studies that say that, usability in this area is, in terms of overall implementations, when they ranked and scored, they said the usability is anywhere between 25% and 40%. So really a lot of work needs to be done, and I think that has been kind of our mantra. Really we don't go in and do the integration work, because we have a lot of specialized consulting houses, the big five consulting houses that can do all that. So our niche is just the usability perspective. So what we are going to do is we are going to look at some major areas, where I have seen the tool being underutilized. What are the powers? What is the power of the engine, and where the areas? Where are the areas that people have not really leveraged the tool? Now, not to say the tool itself has many shortcomings, right? And some of the challenges are with the tool itself, and that's true with any tool, right? SAP has some shortcomings. Oracle Demantra has shortcomings. All of the tools would have shortcomings, but the creativity comes in looking at the shortcomings, looking at the business requirements, and trying to creatively overcome it, right? Because you don't want to throw away a multi-million-dollar tool just because it cannot do a particular thing that you're looking for, right? So on the other hand, if you have the planning books in front of you, and you have the planning screens, you have everything in front of you, but then if you think that you want to use Excel spreadsheets to do most of your forecasting, or an offline tool like John Galt or Forecast Pro, and then load that forecast back into SAP, type in that forecast back into SAP. This is really not for laughing. Basically, I have seen this happen with a number of clients. Some major Fortune 100 companies, I've seen planners do this, right? The IT group will think, it's a successful implementation, but the users will keep their mouth shut. They go back and look at Excel spreadsheets and offline forecasting tools, create the forecast, and load the forecast back into the planning book. And the only reason why they do that is because only if it gets loaded, it gets communicated to S&P, right, for supply chain planning. So that's, in summary, is a tragedy, right? You spend multi-million dollars and users are still using Excel spreadsheets, right? So that really kind of gives you the gap between the power of the tool, business requirements, and usability, right? Excel is very usable, not very powerful. People work hard and use it, right? On the other hand, APO is powerful. There is a gap, but they also think it's not very usable. Then they are not using it. So really the idea is, how do we look at the engine, and how do you look at, what your requirements are, what your model requirements are. So it requires a little bit of understanding of the business, understanding of the models per se. So really the objective in this case is to show you, walk you through APO, APO requirements, APO features, and how this can be leveraged, one version in terms of what we do. So, and some of the stuff is calculations. I think that's another thing that I haven't seen any material, or even within SAP documentation, has done a very clear job of documenting or explaining what these metrics mean and how they are being calculated, right? It's still a black box. I mean, SAP manuals have formulas, but those formulas are not always exactly reflective of what happens in the background, okay? So anyway, so we'll talk about that as well. So with that, let me start. So model diagnostics, right? First of all, I would like to define what model diagnostics mean, right? And we'll do that. Um, Model diagnostics is important to assess the quality of forecast models, right? So the objective is the quality of forecast models. This helps in model selection process. Um, so, for you to assess the quality, you are looking at model selection, model diagnostics. If the diagnostics tell you something, then you go back and redo the model or basically tweak the model parameters to come up with a new model and run this process again. So the idea here is, we are looking at forecast error metrics as model diagnostics, right? We are not looking them as performance measure. We are looking them as to assess the quality of the models, right? So we have worked with MAPE, root mean square error, and MPE. So some of you may have seen this before. Now, MAPE is something that we talked about in detail yesterday, right, in the workshop yesterday. Now, we'll go ahead and define the other measures as well today, right? And the interesting thing is SAP defines them in a unique way. It defines it differently than what you would have thought that it is doing, right? So we'll illustrate the calculations. We'll also look at tracking signal. Now, tracking signal as such is used by SAP in model development, but it does not report it. So if you want to, compute a tracking signal from SAP itself, we need to do some programming in the backend, right? So I'm not going to go into all that. I'm just going to explain for tracking signal to you today, and we'll understand tracking signal and then say, hey, listen, if we need to leverage SAP to do this, we got to do some work, right? We got to spend a bunch of money to some consultants and get that done. Okay, so here you go. Overall outline. So we'll talk about forecast modeling very, very briefly because forecast modeling is what we cover extensively in our principles course, which is our first course. I may have mentioned this. So that is a 2-day course that talks about demand planning, demand modeling, goes into details of demand modeling and covers a variety of models. And then talk about metrics, talk about consensus process, new product forecasting, and also SNOP. It's a 2-day seminar, and the next one we have is being held in May, first week of May in Boston. So here we'll just talk very top line about forecast modeling, and then we'll explain the concept of model fit versus model robustness, right? If you have taken a forecasting course, an academic course, they will also explain what the fit means, what the robustness means, right? And I know when I took my first stat class, when they talked about fit and robustness, my eyes glazed over. I didn't really know what it meant. The word robust sounded very good, but other than that, I didn't know what it meant. But anyway, so I will try to explain it to you as clearly as possible. What's the difference between the two, right? Then we'll talk about demand forecast errors, right? We'll define and we'll talk about, this is the key, in this workshop, right? We'll define errors over time versus errors across SKUs. So yesterday we talked largely about cross-sectional metrics because we talked about performance measurement of a value chain. So we talked about errors over SKU, right? We talked about weighting them. We talked about calculating a summary metric for a division or a group of products. Today, we are more interested in errors over the history of the model, right? Errors over time, but but using an individual, SKU. For an individual SKU, we are talking about errors over time. Okay. All right. So then we'll talk about model errors in APO DP. We'll go through the variety of errors, and we'll talk about outlier adjustments, the type of problems outliers could cause. And finally, we'll talk about the diagnostics, the tools that are available within the tool itself for diagnostics and monitoring. Okay. So that's kind of like our outline today, and we'll also talk about some examples, and I'll show you some screenshots, but it's really not a workshop that will actually make it interactive and show a live APO implementation, right? So you all know that. Okay, so any questions so far in terms of objectives, in terms of the outline? Okay, very good.
I
Now
have a
let me,
question.
go ahead.
I don't know if anyone else out there is having trouble with this, but I'm having trouble getting the GoToMeeting to work. Is there a phone number I can call them at to troubleshoot this or anything?
Oh, you're not able to see the video?
No, sir.
Is anybody having the same problem?
No, I'm okay.
Okay, so if, all right, if any of you have a problem, could you just chat me a message saying you have a problem? Okay, so who had the problem here?
This is Steve Hall at Whirlpool.
Oh, so you're not able to get in. Do you have the password, Steve?
I do. It just says connecting and won't do anything.
Uh-huh. Okay, and are you on a Mac?
No, I'm on a PC.
Okay.
And I'm wired, so it's...
All right, I'm going
I
to
don't
give
know.
you a couple of phone numbers, and then you could call my assistant at the office, and then see maybe she can help you with this.
Okay, great.
Okay, I'm going to type this number in. Okay, that's one number. Okay. See, if not, you could also do...
Where are you sending this phone number? Because I can't see any of this.
Oh, you can't see any of it. That's right. Okay, I'm
No.
sorry. Call the office number, 781-995-0685.
Say that one more time.
781
995.
0685. It should be on the website also. Okay, if others have difficulties, the other thing, Steve, is you can also try gotomeeting.com, but call the office first, please. Okay, all right, everybody else, sorry about that. And, okay, so basically I just also want to stop and ask a question. Does anybody have a view or, any insight into what we mean here between model fit versus model robustness? Does anybody want to venture what robustness means? When is a demand forecast model considered robust? Anyone? Okay, all right. So I will explain this. Okay. So basically, in terms of the model diagnostic process, which I briefly explained before, you forecast with the model. You develop a model and develop a forecast. And then you calculate model error with reference to history. So you just think about how well it fits with the history, and you develop a forecast error, right? It is called as an exposed forecast error. So you just develop error. Error as such is the same formula as yesterday, which is actuals minus forecast, right? So you look at the error in the historical period, right? And the model would have given you a model fit or a forecast number for every point in history. So that's what we are talking about when we talk about model quality assessment. And when we talk about error, so this is an exposed forecast error, or it's also called as a model diagnostic. So we'll explain that. Then we say, hey, that's too high. I'm going to see if I can come up with a different model, right? So for example, if you have a series that looks like this, right? And if you have a model, you pick a model that looks like, let's say this, right? That's your forecast model. So what happens? Obviously, that it is going to report a lot of error because the exposed forecast error is going to compare errors for each one of these points, right? And obviously, just eyeballing it, you would know that this is not the right forecast since the actual model forecast is trending down. I'm sorry, the forecast is trending down. Your forecast is trending down, whereas the actual data tells you that the demand is going up over time. Although it's erratic, it's going up over time, right? So obviously, this is not a good model, right? So one is, you also want to look at this graphically as well. So APO provides the graphical capabilities. Now, that's another thing that I have seen in some of the implementations that we went to re-engineer, that the users don't have the graphics turned on, right? They have never been taught how to use the graphics, right, or what it means. And so typically in the configuration, the graphics were never turned on, right? And it's not part of the training as well. So which actually I think would be a big, it is a big low-lying fruit, if you will, because whatever you do quantitatively, if you're able to see it qualitatively using a graph, that goes a long way, right? So, and APO has graphing capabilities, and it produces graphics. The interface is very similar to Excel graphics. You can do whatever you do with Excel graphs, you can do that with APO also, right? And some of you consultants, you probably specialize in APO, you probably already know this, right? And I would like your viewpoint as well when we go throughout, because I think we have some folks from I believe Hitachi Consulting, right? So maybe some of you have implemented APO. So any thought points, any experiences that you can share would help as well. So then what you do is actually you just take the forecast, you just take the model, revised model, and then do another forecast, right? Then do a model diagnostic again, right? Then do a model diagnostic again. So what happens is this is kind of an iterative process. It's quite possible for any particular SKU or product, you may try 10 different models, iterate through, right? And, sometimes you may improve, sometimes you may get worse, right? And if you think, oh my God, the fourth model I tried looked good compared to the 10th model I'm trying now, is there a way that I can go back to the fourth model, right? The answer is yes, because SAP actually remembers all of these models, right? Of course, it depends on a setting also, right? So if that setting was set up, without any thought during the configuration, then you could have a problem. I mean, you can actually change that setting too. So SAP does remember that, and then you can go back to the fourth model, or you can compare a variety of models that you want, and then say, oh, I'm going to pick the second model I created because that's much better than the other 8 because they have become much worse, right? You can do that. So this is the model diagnostic process, right? So basically going through, it's actually a modeling process, but you're using diagnostics, right? You're using the model error. So the key takeaway is you are looking at errors here, right, over the history or using model fit. So this is called as ex post forecast errors, right? Or these are also called, model diagnostic, okay? So modeling and model quality assessment, right? What is a demand forecast to start with, right? We probably all know this since most of us are demand planners. A demand forecast is an expectation of future demand, okay, based upon experience, past history, okay, reliable within an acceptable range, okay. Yeah, so demand forecast is an expectation of future demand. So it's really an expectation. And for the large part, you are leveraging history. And also, you know that it is not going to be perfect. It's going to be erroneous anyway, right? So if it is erroneous means what happens? It is only correct within an acceptable range, plus or minus 10%. So yesterday we talked about, I believe we talked about expected future error, right? And that's what we call as the confidence of the forecast, right? Or you can think of it as a confidence interval. So based on the history of past forecast errors, you come up with a confidence interval for your forecast or the confidence for the forecast and say, I'm good within plus or minus 20%, right? So I guarantee you my forecast will come within plus or minus 20% of the number I gave you, right? Because the number I gave you is just a point forecast. So think about this. I mean, I think maybe we didn't talk about this. We talked about this using a normal curve yesterday. But think about this. We talked about this using a normal curve yesterday, saying this is the forecast, upper limit, lower limit, right? But if you have a forecast like this, right, that's your point forecast. Then the confidence interval, right, you can just say, hey, it's either plus or minus 20% of the forecast. So what happens? My forecast is going to be, it's not going to be above this or not going to be below this. My actuals are not going to be below this or above this, right? They're going to be within my forecast within this bound, right? So that's the confidence. So it's reliable within an acceptable range, right? Acceptable range. Because if you say, my forecast is going to be within plus or minus 50%, then that's not going to be good information for the supply chain, right? And we also hope that it's unbiased, right? So which means we pick the middle point. We don't pick a point close to either tail, right? We pick the middle point. So which means largely we have a 50% chance of it being the actuals being below as it is above, right? It's unbiased. And then internally consistent. It has to be internally consistent, top down and bottom up. And SAP and other modeling tools as well have have this capability, right? Have this capability. They would allow you to model at any level you want. Of course, you have to do some settings in the configuration. They will allow you to do any modeling at any level you want, and you can use that modeling, and then you can proportion the forecast down to lower level forecast units, right? So if you're forecasting at the brand level and you say, I want this forecast to be drilled down, proportioned down to my SKU level, then you would do that, right? You can do that because the proportions would be built. So there is a variety of proportioning logic that's available as well. And this you can also I promised you a white paper reference as well, and I will make sure that I send all of that to you by tomorrow. So I promised you about the forecast accuracy. There is also a link where you can look through some literature on the on the proportioning as well, right? Not with reference to SAP, but generally like what is the logic that's available. So regardless, it has to be internally consistent, right? If you add all the forecasts from the SKU to the brand, right? There should be a clear way that they add up. So if you extract numbers at the brand level, they should be the same as the sum of the numbers at the item level that rolls up to the brand, right? So it has to be internally consistent. You cannot give a forecast at the top level that's different from the sum of the numbers at the bottom. And remember, we talked about this yesterday also. We talked about the financial forecast aggregated level is different, or it's lower than the sum of the item level forecast. So which means that forecast is not internally consistent, right? So these are the various features of a demand forecast, right? So then we say, okay, well, that's good, but we use a model to develop a forecast, right? And I think some of you may have attended. I think a few of you attended the other workshop, the CPG workshop as well. So we talked about this. A model is a mathematical representation. So it's an equation that explains the relationship between different forces affecting demand, right? Okay, different forces affecting demand. So typically, left-hand side equals right-hand side, right? That's the two sides of the equation, and that's a model. So a model is nothing but a mathematical equation, right? So in our case, a forecasting model says left-hand side is always future sales for the item, product, brand. Right-hand side is past sales, right? Which is an average of the past history of observations, and this is called as the level component, right? Patterns in sales, right? Whatever pattern happened, it could be trending up or down, and it could have seasonal peaks and troughs, right? So this is the patterns in sales. So this actually includes trend, okay, and seasonality. Okay, trend and seasonality, right? And impact of new information, right? That's the third piece. Now, before we go into impact of new information, because we're not going to talk about that today, because we're not going to talk about any causal models, right? So impact of new information can be captured using causal models, right? Or intervention models. And you can do causal models in SAP, although SAP APO is not a very powerful tool for doing causal models, right? You can do some simple models, but it's not a very powerful tool for doing those. But so today we are talking about these three. So in here, right, if you have taken the principles course, or if you already know a little bit about forecast modeling, then you say, I have actually done exponential smoothing before. So if I use exponential smoothing, I actually can model the level component with what is called as the alpha parameter, right, in most exponential smoothing models. The trend component by what is called as the beta parameter. The seasonality by what is called as the gamma parameter. So basically our model is, well, you're going to take the level and you're going to take the trend and seasonality and come up with a forecast model, right? So basically you will have a level, which is an average of the past, right? A trend if it is going up, right? And then you will have a seasonality, right, which actually says, it's going up and down over a period of time, right? So basically, that's what you have. That's your final forecast. That includes all of the information that you have observed from the past, from your historical time series. So what are the models we have? This is the large family of models, right, that are available. And we will talk about which ones are available within APO, right? So there is the first set is called as the univariate time series models, right? Univariate time series models. And these models just use historical information, historical past of the same variable that we are forecasting. If you're forecasting volume, it is just going to use volume to come up with the forecast. And in the previous slide, right? In the previous slide, this is, if you are modeling these two, then you are just using univariate time series models. Just time series models. You are not modeling impact of new information because you cannot, right? So that's univariate time series models. So these include, right, averaging, just simple averaging. If you think your demand profile is definitely flat, I think yesterday Michelle, I believe, was talking about, flat demand profile. So if you think your demand profile is flat, you can just use simple averaging. You can use a moving average or an exponential smoothing model, right, which will still give you a simple exponential smoothing. You can use smoothing models, right, like more fancy smoothing models that will give you patterns as well. You can also use deterministic time series regressions, right? And this is available in APO also, right? And it is also available, and it's called as the time trend models, right? And you can also use ARIMA models, right? Now, here is the thing. So basically, ARIMA models are a more advanced variety of statistical models, autoregressive integrated moving average models that are dynamic, more powerful models, right? Because the smoothing average models, or the smoothing exponential smoothing models, only exploit the moving average component, whereas the ARIMA models exploit both the autoregressive and the moving average component. So let's not get into too much, technical detail here, right? And then you have causal models, right? Causal models are multivariate regression models, right? So these, use a causal variable. Like, for example, forecasting your sales as a function of, let's say, the heat index, right? How hot it is, right? Average monthly temperature, right? That's a causal model, okay? Forecasting your sales as a function of the economy, right? Or interest rates or something like that, right? That's a causal model. Now, SAP can do that to a limited extent, right? These are not very powerful. They just do simple multiple linear regression models. They are useful to a certain extent. As a statistician, if I am just doing causal models, multiple linear regressions would be a very small part of my toolkit, right? So anyway, the idea is it is there and you can leverage it, okay? And then finally, you have subjective methods like, the other, which is judgment-oriented methods, okay? So basically, if you think about it, APO-DP has univariate models, right? And also MLR models, multiple linear regression models. And you would see, if you go back to your profile screen, you would see univariate profiles, multivariate profiles, right? That's how you distinguish it. And then you also have the other, and this is what we call as the composite profile, right? So if you go to the master profile screen, you would see univariate profile, multivariate profile, and composite profiles. And you could do manual adjustments in APO because there is also a manual adjustment model available too. So we'll cover we cover a lot of this on, our APO DP on-site training course, which is much more detailed. It's conducted over a 3 to 4 day period depending on, what the requirement is. And it's a customized course. It actually goes into the, basically we look at the, configuration, we, carve out examples, we do some business process work in terms of business diagnostic work, and then that's what we incorporate into our material. So that's the reason why this APO course is not offered as a public course because, our philosophy is it really depends on a individual client implementation. So there is really no point in doing an, overall APO, just regular training course and navigation course if what have you, because that's being taught by a number of other people. and that has limited usability because you go to a public course, you go to Atlanta to the SAP Institute, take that course, and then you go back to your implementation, and you have no idea what you learned versus what is there, right? So we offer this as a customized on-site training course that is really specific to the client's implementation. Okay, but we cover all of the stuff there. Now here is a quick question for you. Now, of the models that we mentioned here, right, and I assume most of you have used APO. Of the models that I have, you have seen in SAP, which model family or which model do you think is not there in APO? Any responses? Anybody? You can chat privately if you want. Okay, there is one model, one family of models is not available in APO. Okay, let me ask you, how many of you have worked with or are using APO at the present time? Anybody not using APO or entirely new to APO? Okay, folks from Abbott, are you using APO today? Okay, so all of you are using APO. Okay, all right. What about folks from Medtronic?
Yes, we're using APO, but I personally do not use APO.
Okay, I got you. All right, very good. Okay, so you're basically trying to learn this before. Okay. All right. Okay, very good. So basically, any thoughts on which model family is not available in APO? I mean, all of these are available in APO, except ARIMA models, right? These models are not in APO. Okay. Causal models are there in APO, but transfer function models are not there, but causal models, particularly MLR models are there in APO. So this is the only family that's not available today in SAP APO. Okay. All right. So qualities of a statistical forecast. Now, I think this is a very important concept to learn and understand and keep in mind, especially if you are a modeler, a demand planner, right? A good statistical forecast is characterized by, we just need only one is there. Best fit of historical demand data, important quality of any model, right? Best fit, right? And what do we mean by best fit? A best fit is a model that really gives you a very good fit, a decent fit of the historical data points. So you use a model to forecast, right? And when you develop the model goes through an iterative process trying to fit it with the observations. And if you look in APO, APO would provide you a chart, right, in the graphics. It'll provide you what is called as an ex-post forecast, right? A forecast for the history. Now, if you think about this is a pretty decent fit, right? Because it covers, on average, all of the actual data points pretty closely. It is still missing some, but it's close, right? Because there is still errors for some of these, right? These are not right on the model, and it's not expected to be, right? So that's a best fit historical demand data. So if I just tell you, what, I have an alternate model that I can take a look at, right? Let me use something else, right? So an alternate model looks like this. Now, which model is better? Obviously, this model is better because it provides a better fit of the historical data points. So a good statistical forecast is characterized by best fit. So in reality, in model terminology, statistical terminology, the fit is measured by the R squared of the model. So R squared just tells you the degree of explanatory power, right? So basically it is called as the model, degree of variability, right? Explained by the model. Degree of variability explained by the model, right? Divided by total variability, right? So basically, you can think of this as, okay, well, I have all these variations. How much is my model able to explain, right? That's what R squared is, right? So in this case, when I look at this, I would guarantee you the R squared is probably greater than 90%. right? The R squared is greater than 90%. Okay. So best fit, R squared is one of the criteria, right? Robust, fairly stable over time, right? And I cannot emphasize the importance of this particular quality, right? Or character of a stat model, a good stat model. Robustness. Robust is very key. Is an important aspect or an important attribute of a good statistical forecast model. Your model should be robust, right? Fairly stable over time. So what does that mean, fairly stable over time? So which means the model does not change its character or direction completely just because you got one data point, one new historical data point last month that had a high error, right? The model does not change just because of the most recent observation that was different from the model, right? It's fairly stable, right? It's fairly stable. So if you think about this, right, of course I put a forecast model that's kind of a little dummy here, right? But if you think about this, the robustness, right, means that the model is stable and the model is more predictable over time, right? More stable over time, and it does not change or vary too much over time, right? So if you think about an alternate model here, right? Let's say we just go with an alternate model that looks like this, right? Now think about this. This model is actually slightly better than this model, right? Because at least it's actually cutting through the data points and it's in the middle, right? Now, in terms of robustness, right, this model would be fairly robust in the sense most of the forecast is actually a straight line, right? The adjustment would be slightly off, right? Whereas this model would not be as robust as this one because this model would change depending on what the observation is more recently, right? So the idea is, you can achieve a good historical fit, but doesn't guarantee that the model would give you a good forecast in the future. The reason being, the model may not be robust, right? You can achieve a good historical fit, but that doesn't mean you have a good model to forecast into the future. So more a model is robust, then it means you have a better chance of a forecast being better or higher in accuracy, right? So if you have to balance the two attributes, right? It has to be a good fit. It doesn't have to be a perfect fit because the moment you have a perfect fit, there should be a red flag there. If you think a model reports an 100% error, right? And if it's a perfect fit, that actually means that you have a problem, right? It may not be robust and you will have problems in the future, right? So if you balance the two, then you say the model has forecasting power, meaning that expected forecast error is low, right? Expected forecast error is low, right? So if you think about this, right, fit versus robustness, fit is determined by comparison to the history, concept of exposed forecasting. Closer your model to the history, the higher the fit. So which means R squared is also higher, right? Robustness is determined by model stability, how stable the model is, meaning that it's not yo-yo. It doesn't change too much just because of the last observation, right? Fit and robustness are both important. Chasing model fit may compromise robustness, right? That's a key takeaway here. So if you are chasing model fit, right, then it actually may result in compromising robustness, which means you cannot just say with any guarantee what the future is going to be. On the other hand, if you choose a very stable model, may result in inefficient models, right? Models that do not explain history very well. As I explained to you before, a straight line model is very stable, but it's inefficient, right? Because it doesn't capture all the information in the history. Although in the previous case, if you look at it, right, the history it didn't have a trend, but it had seasonality. The straight line model captured the average, but it did not capture the seasonality information already in the data, right? So you need to make a trade-off between robustness and stability and model fit, right? So I can give you another example here, right, before we go into ex post and ex ante forecast, right? Okay, let me just give you an example. You may have heard of neural network models, right? So this is not a criticism of neural network models, but let me just give you an example, right? Let's say your actual looks like this, right? Now, you can always come up with a model, right, that looks exactly like this. It matches all points, right? It matches all points on history, right? So you can always come up with this. And there is a technique available in APO also to do that, right? And that's called as using the historical profile. So if you say, hey, listen, my next 1 year is going to look like the last 1 year, right? Obviously, it's going to repeat that into the future, right? So if you come up with a model that exactly matches all historical points, what is going to be R squared? It's going to be 100%, right? I mean, pardon my graphics here. The idea is the red line is supposed to be on top of that gray line, right? Dark gray line. But with this, now, how are you going to forecast this, right? Is the next thing going to be here or here or down? We don't know because this is actually pretty chaotic, right? We don't really know what it is. With this model, we cannot forecast anything. But on the other hand, if I just use a model, because all I know is, I look at it, to the naked eye, it looks like, okay, it is trending up. That's all I can say. And seasonality, I think it's really chaotic. I don't really think there is a seasonality here, right? Maybe every 3 months it's actually going up, perhaps. But then there is no seasonality here, right? I mean, there is no trend here either. So basically, all I can do is I can come up with a trend-based model in the future, right? Now, this model is fairly robust, right? Because you can actually forecast with this model rather than the one that exactly mimicked the history, right? So really the idea is you need to kind of balance the two between robustness and fit, right? So if a model is very robust, if the model is very robust, then the idea is you can actually come up with a guarantee of how the forecast is going to be in the future. So just balance the two, model fit versus robustness. So even if the robustness concept is not that clear to you yet, I would say, just use this takeaway. This is an important takeaway, right? Chasing model fit is not always a good thing, right? Trying to pick a model that actually fits the historical data perfectly means it's a red flag, right? You have to cautiously think about that model. You don't want to look at a model just because it fits the history so well, because it will just totally bomb out in the future, okay? All right, question. Okay. Um, okay. All right. So there is a question that I will answer in a minute, but let's move on here. So ex post and ex ante forecast, right? So ex post forecast, right? Ex post forecast is forecasting the history, right? So let's say you are in January 2009, right? So ex post forecast means, right, it's really measuring model fit. So this is ex post forecasting. If you think about this ex post forecast, actually this model has matched a lot of points, right? It still has left a few points out, right? Because it's a model. It's just trying to give you a forecast in the future. See, think about it. A model is a mathematical formula, right? So if you write a mathematical formula that looks like this, y equals a plus b times x, let's say, right? That's your model. So which means for any given unit of time, you should be able to forecast y, right? Because this is a model, and this is child's play. If you give the formula to any sixth grader, they would be able to compute the forecast in the future because it's easy, right? So at the end of the day, a model is going to result in something like this, which may be a little bit more complex formula. Regardless, it's a formula that you can use to forecast in the future. But on the other hand, if you artificially try to match all these points, then it may be very difficult to write a formula like this, or the formula that you write would be very contrived, right? So which means it is also difficult to forecast that for extreme points in the future, okay? So here, this is the ex post forecast. So what APO does is, APO calculates all the error measures with reference to the ex post forecast or the model fit. Most of the error measures APO calculates, and take it from me, most of the model diagnostic is all based on ex post forecast, is all based on historical data and the fit of the forecast to the historical data, right? Now, ex ante or ex ante forecast is just the real forecast in the future, right? Think of this as 2009 is future now because, we are in 2008, right? Let's say we are in December 2008. Okay, we haven't changed all the stuff because we can't keep changing this. So this is the future period, forecast period. So the forecast for which you don't have any information, right? That's what is called as the ex ante or the future forecast. Ex post forecast is just forecasts of the history. So all of the diagnostic measures are computed with reference to the ex post forecast, comparing the actuals with your model fit, right? This line is called as a model fit, comparing the actuals with the model fit, okay? So think about this. Forecast errors, fit versus stability. I think I may have given you a hand-drawn ugly chart, but here is a real chart, right? So let's say here is your actual data. This is your historical data, okay? So now your first model was a straight line model, okay? Let me see if there's additional questions there. Okay. The first model is a straight line model. So this is your first stab at it, right? It's a straight line model. What does it capture? It's an average of all the data, right? So if you think about this, this is a stable model, right? Because it's a straight line model. Next period is going to be, again, straight line. Maybe it's going to adjust a little bit up or down, but it's going to be very stable, right? So now, but this is not a very efficient model because constant model with better stability. So this is more stable. But on the other hand, these are the errors, right? Because the error, this is the actual observation. This is the forecast, right? So that is the error of model 1, right? This thing is the error of model 1, okay? Now let's say IPO computes are with actuals compared to the model itself in the historical period. And that's what we're going to look at today, okay? All right. So we'll jump into error diagnostic here, okay? And at this point, I also want to see if there are any additional questions here. Okay, there is a question on APO. Actually, to tell you the truth, APO does not have any ARIMA models at all, right? And the alpha, beta, gamma parameters in APO, basically that we talked about, the alpha, beta, gamma, model the level, trend, and seasonality component just in exponential smoothing. So these are all exponential smoothing models, right? So now you can compare exponential smoothing models to ARIMA models. If you think of ARIMA models as models without any autoregressive component, right? If you just use ARIMA models with an MA component, then that would just like break down into an exponential smoothing model, right? But if you're, so idea is even in reality, even if you have ARIMA models, but if you think a model can be explained with just moving average component, exponential smoothing component, then I would prefer exponential smoothing than ARIMA, right? Because ARIMA models are complex. The thing about ARIMA models is ARIMA models cannot be intuitively explained also, right? Exponential smoothing models can be explained. But ARIMA models are powerful because you can do a variety of causal models using what the technology called as transfer functions. So I don't know, maybe some of you are mathematicians here. So, what is called as transfer functions, and that really would help you look at, look at causal variables. You can use causal variables, and that can be used to model your forecast as a function of, like, say, heat index, that type of stuff, or even for intervention models, okay? All right. So, okay. So forecast error is defined as actual demand minus exposed forecast, right? That's what APO defines it, right? Actual demand minus exposed forecast. Sorry about the annotation there. Let me just get rid of that annotation. Okay. Okay. Forecast error is defined as error minus error is equal actual demand, right? Minus exposed forecast. Okay. So this we all understand. That's what error is. But the difference is this exposed, the term exposed, which means it is comparing the historical observation with the forecast for that particular historical observation. That's what exposed is, as you saw from the previous slide. So that's a big difference between how we define error yesterday versus today. In yesterday, what we did was we looked at the forecast, right? But that was an actual forecast because it was a forecast version made 2 months ago or so with a lag, but was really a forecast of the future. But today, we are looking at the forecast made today for the past, right? It's a forecast for an historical observation. So there's a big difference, right, between what we talked yesterday and what we talked today. Error is error, but still what we're using is different, okay? So these are also called as in-sample forecast errors, right, or historical forecast errors. These are in sample because if you have 30 months of observations to model the future, you have sample size 30. You're using a history size of 30. Now, this is another thing that I've noticed as well, and this question came up in our CPG seminar. I don't remember, maybe yesterday, about the number of historical periods that are available in APO. And I have seen IT departments being very ambitious, and they chop off the history. So they're just like they leave only the last 24 months to model, right? They don't, they basically, they just think 2 years is enough, or maybe 1 year and some months are enough, that type of stuff, right? Although history is available for the last 4 or 5 years, they don't really give, use all the history, right? So that's another thing, right? Because if you think about it, if you have history less than, say, 3 years or 30 months, let's say, you still have difficulty statistically coming up with a robust model and a forecast that will be powerful, right? So I know that, sometimes it may not be feasible to have a lot of history, but if you have the history, you may as well use it instead of, somebody in IT deciding that it's not a good idea to use it and chop it off, and then the users only have the last 24 months. Because, within the system itself, you have the ability to use the right history that you want, okay? So, so they are the result here. It's in-sample forecast errors. They are the result of forecasting the history. The model diagnostic is an average of the error comparison over time. So it's not just one observation. It is computed over a large period of time, okay? So error diagnostic calculation is nothing but, here is the actual demand, and this is your forecast, and this distance measures the absolute error, and then your diagnostic is an average of all of these distances, right? Now, sometimes it could be distances, sometimes it could be netted values, especially because APO diagnostic also includes a diagnostic for bias, right? Model bias, right? If the model is, either under forecasting or over forecasting history significantly, that will also, the diagnostic will tell you that, okay? So here is where we make the key distinction between yesterday and today, right? Errors across SKUs versus errors across time. Now, this can be a cause for confusion also, right? Because sometimes you try to relate what your monthly KPI forecast error is to what the model error is, right? And there may not be much relation there. Cross-section for one period across many SKUs, right? So we take one period, which is last month, and measure it across multiple SKUs. So this is a measure of forecast performance, and we talked about this yesterday, value chain performance, right, of the planner, the demand chain division as a whole, and this is what we talked about yesterday, right? And it has its own challenges, and we talked about all of these challenges in detail yesterday, and the biases and some of the other issues, game playing and all that yesterday. So it's a summary measure for a single period across all SKUs. So, a CEO can call up a division and ask him, hey, what's your forecast accuracy last month, right? What's your MAPE? And if they do, that'll be great, right? If they do, then the division manager can say, this is how we forecasted last month. There is one number they can say for the entire division. So it's a measure of forecast performance. So one example is the MAPE across SKUs, and we talked about this in detail yesterday. So it's used in the S&OP scorecard and also the reporting, division KPI reporting. Calendar errors is error for one SKU, right? Error for one SKU across many periods. So you take the same SKU, right, and then measure the error every month in the past, right, and take an average. So this is also called as the model error or error diagnostic. Okay, model error or error diagnostic. So used to measure the performance of a model and revise the model or process to forecast the SKU, right? Forecast the SKU. The example is, a root mean squared error over time for the same SKU or MAPE over the same SKU, that type of stuff. So the interesting thing is nobody else cares about it. Only the modeler or planner, the demand planner for that particular SKU cares about this error number. Plus, there is one more person that will care about it, and that would be the supply planner for that particular SKU. He will care about it because the supply planner would look at this error for safety stock calculations, right? And they would like for the demand planner to communicate some type of average performance of the SKU over 6 months or so to them so they can use that for safety stock calculations, right? But this measure, nobody else worries about it. General manager doesn't worry what your model error is for a SKU, right? He's not worried about model quality. He's worried about an accurate forecast at the end of the period. He doesn't care what model he uses, right? And it's not a measure of his performance. The president of the company doesn't care about this. So the only person that cares about this is the modeler or planner, and with a one selfish objective to improve the quality of the model, to improve the resulting forecast, right? Of course, everybody else cares about improve the resulting forecast, but they don't care about how you arrive at it, right? I mean, actually, in essence, people shouldn't really care much about how you arrive at your forecast if your forecast is accurate, right? And particularly supply planners and managers, they can actually give you suggestions. They can ask you to use POS data, talk to the sales guy, talk to the customer team, work with Walmart, Retail Link, what have you. We talked about all of this stuff in the CPG seminar. But at the end of the day, the planner cares about this, and they improve the forecast. So you may want to think of this model diagnostic as model specific, SKU specific, planner specific, and this varies from SKU to SKU. And also another thing, there is really no point in aggregating these model diagnostics across SKUs. It wouldn't make any sense. It'll be apples to oranges. A model diagnostic is for each and every SKU. Okay. So, okay, I think that was a repeat. Okay. Okay. So now the next stuff we want to talk about is deviation versus direction, right? Deviation versus direction. Deviation is the absolute errors, right? Is the magnitude of the error. It's a distance, right? So it reflects volatility of the demand as well as estimating accuracy, right? How volatile the demand is. That's one thing. And then how well you are able to estimate it, estimate the volatility itself, right? So deviation is important, and there are diagnostics that would tell you how good the model is based on the absolute errors. And there is model bias, right? Direction. Direction implies bias if persistent over forecasting or under forecasting. In the previous case, when I mentioned, your history looks like this, right? And then you have a forecast that looks like this, right? What happens? The forecast is obviously biased. It's downward biased, right? And the bias is going to increase over time because the history is going to go up like this, right? Forecast is going to go down like this, right? So the bias is going to increase over time. So this type of a measure would clearly tell you if there is a bias in the forecast, right? If there is a bias in the forecast. Okay, so let's now jump into reviewing the APO error metrics, okay? We'll jump into reviewing the APO error metrics here. Okay, so far, do we have any questions? Let me stop for a minute here.
How do we go about getting a copy of this presentation? Will that be sent out after the discussion's over?
Yes, absolutely. We'll mail you the copy of the presentation. Yes. It'll be, you'll be able to download this. Yes, we'll send you the link and all that to download it. Yes.
Okay.
All right. So, any questions so far? Okay. All right. Very good. So let's move on here. APO modeling error metrics, right? So APO reports 6 error metrics with its own custom definition of each, right? Actual demand, error is actual demand minus exposed forecast. I mean, we knew that, right? That's what it uses, right? Now, these metrics can be used in forecast system alerts. All 6 can be used. But actually, it's meaningless to use all, some of them anyway. Some of them cannot be used in alerts, but, that's what APO says, that you can. But although APO uses common terminology, calculation method is unique, right? Now, of the 6, the 3 most useful are these 3, MAPE, MPE, and RMSE. MAPE stands for mean absolute percent error. MPE stands for mean percent error. And RMSE stands for root mean squared error, right? And we talked about this yesterday, right? But when we talked about this yesterday, we also said the way that I had explained to you to calculate the MAPE as a performance measure was in reality a weighted MAPE, right? And it's weighted by the volume, right? As a performance measure cross-sectionally, we said it's weighted by volume. But, APO's error measure, right, is not weighted by volume, right? It's a simple average of absolute percent errors, just as it says, right? It's not what supply chain planners use for performance measurement for KPI reporting, right? WMAPE is what we use for KPI reporting. As far as I've seen, we have consulted with a number of companies, companies that have, incorrectly used the KPI reporting, which we have corrected. I can tell you almost 99% of the companies that we have consulted with, they all use WMAPE correctly, right? And, there are a few issues that we could have fixed, but all of them had the idea that, hey, if you do a MAPE, it's a weighted MAPE, right? It's volume weighted MAPE, right? And, so basically, because we have worked with a large number of companies, and, I'm pretty sure some of the consultants here would have worked with other companies as well. So supply chain performance, KPI reporting, people get it. They use volume weighted MAPE, right? They understand the Pareto, volume importance of in the volume Pareto, right? It's all volume weighted MAPE. But for modeling purposes, you don't have to weight by volume. If you weight by volume, it's fancy, but you don't have to. So APO uses an average of the absolute percent errors for model diagnostic. That's fine, because the idea is, within the same SKU, there may be volume weights issues if it is a highly seasonal SKU, but most of the time the scales are going to be very similar, right? So it's okay to use average percent error. It also uses a mean percent error. So this is actually what we use it for bias, right? Because it allows offsets for positive and negatives. And another error is a root mean squared error, which is actually an excellent error because it really now includes the weighting. So the weighting, volume weighting, takes place when you use the root mean squared error, right? So that's the difference. This is unweighted. This is weighted. But they both measure absolute errors, right? MAPE and RMSE measure absolute errors, right? They both measure absolute errors. This one does not measure absolute. It's a directional measure. So of the 6, if you know the 3, you are 100% there, right? So the other 3 are, useful in a minor way, but not a big deal if you don't even know them, right? So what are the list of errors? So there are monthly errors. Error calculated each month for model diagnostics, okay? So what is called as a mean absolute deviation. It just calculates the mean absolute deviation. Now, this is used in calculating the MAPE or the root mean square error, right? But it's not used, as an individual metric. You can't really work with it much because it just is a number, right? It'll say the number is 55,000, 848, right? And I'm not sure what you can do with it, right? So that's what MAD will be, right? And it also calculates a tracking signal based on the MAD, but it's not reported, right? MAD is mean absolute deviation, and we'll talk about all that, right? And then the average calendar errors over the entire period, right? Which is an error total, MPE, MAPE, mean squared error, root mean squared error, right? Now, this is basically, this is plain useless measure, right? I'm not even sure why it's there. I mean, this is, the root mean squared error is really nothing but a square root of MSE, right? MSE is like an insanely large number. It'll be like, your volume is 55,000 on average. The mean squared error would report like a volume of 25 million units, right? I'm not sure what you do with it, right? So average calendar errors are computed over the entire period. This is calculated for each month. So each month it's different, but this one is averaged over a large number of months. Okay. So mean absolute deviation, traditionally defined as the average absolute deviation, right? So, but in APO, so if you look at a statistical textbook, a MAD would be, right? A MAD would be defined as an average 1 over n, right? Times, okay, absolute deviation, which is actuals minus forecast. So you would add all absolute deviations divided by the number of periods. That's the traditional definition. APO defines it a little bit differently, right? It's a weighted average of current and past deviations, similar to exponential smoothing. So for every period, there is a different MAD, right? So every period, it actually takes a 30% of the current month absolute deviation, right? 30% of the current month deviation, right? And then uses 70% of the calculated MAD from the previous month, right? It uses 70% of the calculated MAD. So it's actually doing a weighted average MAD. So which means it puts more weight on the deviation in the last month. And specifically, it uses 30%, right? Specifically, it uses 30%. Now, here is the challenge, because in some of the models, it may use the alpha that you specify. And the alpha may not be 30%, right? But for reporting, it uses 30%. So anyway, the formula is this, right? It uses 30% of the most recent observation, most recent mean absolute deviation, right? So that's what it uses, 30%, right? The other 70% is based on the calculation you made in the last month, right? That's what MAD is. The reason why we talk about MAD is MAD may be useful in some instances while you're modeling, right? Or when you're looking at the model, because especially if you're using exponential smoothing, mean absolute deviation may be useful to know how it's being calculated. And tracking signal is also calculated with reference to MAD, right? But for the diagnostic today, we are not going to use MAD much. If you're using tracking signal, if you're a consultant that can program in the background, then you may just say, I'm going to do a macro program here. I'm going to look at MAD and then do it, okay? So if you look at this formula here, right, this sheet should tell you, right, what the MAD is, right? The MAD is, 17.98 for the last period, right, which is 30%, right? 30% of the actuals minus forecast, right? That's what the MAD is in this case, right? Absolute deviation is 25, right? And you know the absolute deviation, right? Actuals minus forecast gives you this number, right? 75 minus 100 is minus 25. 72 minus 90 is minus 18. You take an absolute deviation, right? So traditionally, statistically, you would come up with an average of this, and that would be your MAD, 22.8. But for SAP, that's not the MAD, right? So the MAD changes every month, right? So the MAD that you look at in May would be 17.98, and that is the MAD. And that MAD is computed based on 30% of this, right? And 70% of this 14.97. And that's what they compute as MAD. So it actually just like weights only 30% of the last observation. So in some sense, it doesn't overstate the MAD based on the last observation being either high or too low, right? It doesn't dramatically change because, in this case, if you think about it, it's 22.8, but SAP's calculated MAD that it reports is 17.98. So, I just wanted to explain to you behind the scenes what happens. Take it for what it's worth, whether it's useful or not, depending on whether you do some programming in the back end, okay? Okay, so that's a good question. So, the question is, how do we use MAD, right? So my answer is, in terms of model diagnostic, we don't want to use MAD. That's my answer, right? We don't want to use this MAD number to improve forecast accuracy. We can use the MAD number in one area when we are looking at relative comparison of models, and I will tell you towards the end how we use it, right? How we use it. And, I think it may be, that is coming up towards the end, right? We'll tell you how we can improve the forecast accuracy, because this number would change for each model iteration. So you would do a comparison of models, okay? So I will, that's a good question. I will respond to that at the end, okay? All right. So remember the two measures that we talked about? One is error total, right? Error total was one of the measures. That's the total of all absolute deviations. And MAD is the mean absolute deviation calculated by SAP. Okay. So if you go back to the number of measures, right, we talked about error total and mean absolute deviation, right? So error total is the sum of absolute deviations over the historical period, okay? All right. But that's basically error total is the sum of all historical errors, right? So now we'll talk about MAPE versus MPE. Now this is actually, these are good measures in their own right? So this number, MAPE, is mean absolute percent error, right? So MAPE is calculated as average of the absolute percent errors, right? Take the percent error of the absolute error, average it. It's always positive. This is a measure of overall model quality. So can we use this to improve forecast accuracy? Absolutely. How? If you think the MAPE is too high, you come back to a different model. You come up with a model that says the MAPE is 65%. You go to a different model, MAPE drops to 40%. You go to a third model, MAPE drops to 30%, right? A fourth model, MAPE drops to 20%. A fifth model, MAPE drops to 0%. So which model would you pick of the five? It's a trick question. I would pick this model, not this model, right? The reason being, this model is just something that may not be stable, right? But anyway, the idea is lower the MAPE, the better off you are. But you want to use judgment, right? So overall, directionally, of course, the lower the MAPE, the better off you are, right? It's quite possible that you have a very good model that has a MAPE of like 1%, 2%, what have you. I'm not really trying to challenge you or lead you in the wrong direction. So generally, you would pick a model with a lower MAPE, right? Of all models, whichever model gives you the lowest MAPE, pick it. But just make sure that that is a robust forecast, because if the graphics do not look very stable, then think about it, right? So I'm not saying you should absolutely go pick the lowest, but directionally, the lower the MAPE, the better off you are. So, if you think the MAPE is too high, you would remodel it, right? And you can improve this right away to improve model quality. So initially, you would look at MAPE, right? MPE gives you the bias, right? So average signed percent error, right? Instead of absolute value, you get rid of the absolute value sign. Can be positive or negative. Negative means over forecasted, right? It's a measure of forecast bias. So you would just look at these two in combination when you do a model, right? When you do any model, you would look at MAPE and MPE, right? And you can see them. And if the profiles are set correctly, and if you have, I think the other thing is, like, some of the users do not have the authority to change master profiles, right? But if the profiles are set correctly, then you would be able to pick what error measures you want to see in your model diagnostic report, right? So in that case, you would be able to do, you can look at these two on the same screen and then say you're going to remodel, okay? All right, let's see if there are any other questions here. Okay, all right. So look at MAPE versus MPE for an unbiased forecast, right? So, you have the forecast here. The forecast is the blue line, right? Actuals are these points, right? So if you look at a model, this is the model, right? So if you look at a MAPE number, right? a MAPE number, your MAPE is here, right? Your MAPE number is the red line, right? And your MPE number is this line, right? So what's happening here, right? What's happening is your MPE number is actually close to 0, right? On the right scale is close to 0. Actually, ignore the scale. I think the scale is off here. But so your MPE is actually, because the MAPE should always be positive, right? Running MAPE should be positive, right? So the MPE number is pretty close to 0, so which means MPE close to 0%, right? Above and below 0% means it's not a biased forecast. So MPE may be above for some periods, below for some periods, and it means it's not a biased forecast. But on the other hand, if your MPE is somewhere here, let's say your MPE is somewhere here, right? So which means your MPE is always like 15% every month, then that means, you have a biased forecast, okay? You have a biased forecast. Okay. There is a question, I think that's a good question. If MAPE is widely accepted, right, form of error of accuracy, if MAPE is why is it not available in APO instead of MAD, right? MAPE is available, right? MAPE is available in APO. MAPE is available. The only difference is it is not absolute error, right? It is actually a percent error. So it's not weighted by volume. That's the only difference. And which I think is not a big deal. And you can always make it up by using another measure, which I'm going to talk to you about, which is actually much more robust measure, the root mean squared error. Okay? All right. So the MAPE is close to 22%, right? The MAPE is close to 22%. MPE is close to 0%. It's an unbiased forecast. Okay? So next we are going to talk about the root mean squared error. The root mean squared error is the average of the root mean squared error gives you the weighting that you are looking for. So it weights all the absolute errors, right? It weights all the absolute errors. So how do you compute the root mean squared error? You take the mean squared error first, right? Which is the average of squared errors rather than absolute numbers, right? And then, you take a square root of the mean squared error. Gives you the root mean squared error, right? And this is a very powerful, very useful model diagnostic anywhere and also in APO. So thank God this number has been correctly defined, right? So we can use this very creatively, very productively for our purposes, right? It has one shortcoming, which we'll talk about, but that shortcoming is there for anybody. It's not an APO-specific shortcoming, right? Because the root mean squared error is not relative. It's actually a number. It's scale dependent, right? So regardless, this number is also used in inventory management, right? So if you have a root mean squared error number and if you give it to your supply planner, they'll be very happy with it, right? Because this number enters your safety stock calculation directly, right? For some of you, you remember safety stock, work, right? Basically, it's just a sum of forecast error times lead times and customer service required and all that. And the forecast error exactly is this root mean squared error, right? So mean squared error is nothing but the actual observation minus the exposed forecast but you square the term instead of taking absolute values. You're not taking absolute values, you are squaring the error, right? Summing the errors over all the observations, you are adding them up over all the observations and taking an average divided by the number of months. So for 30 months, you would say n is 30. So you come up with the mean squared error, right? Then you have the root mean squared error, which is nothing but the square root of this number, right? So this in APO, I would say, is actually the best model diagnostic of all the 6. The most useful, the best diagnostic, right? Now, the only thing is this can also be used only with reference to a comparison of models, a comparison report, right? And that's the reason why you need to be able to look at the comparison report that compares all the last 20 models you did, right? That's the only shortcoming, because the root mean squared error is not a percentage number, right? Is not a percentage number. Whereas the MAPE and the MP are percentage numbers, right? Because as humans, percentages make sense because they're relative, right? We can say, 50% is too high, 20% is better, 5% is even better, right? That's easy. But root mean square error is going to give you a number in units. So it's scale dependent. For one SKU, it will be like 55 units. For another SKU, it will be 3,000 units, right? It will be different. But fortunately, we are not making SKU to SKU comparisons. We are making comparison between models for the same SKU, okay? All right. So let's just talk about the illustration here. And basically, if you look at it, there are 5 months here, right? Pretty much same illustration as before. So you take the error, absolute deviation, right? And then you take the squared error, right? This is the squared error. You square 25, 625, square 18, 324, square 45, 2025, and so on. Sum of these squared errors gives you 3,600. This is the sum squared errors, right? Also called as SSE in statistical parlor, right? So basically, you have SSE. And then you take an average of this. 3,600 divided by 5 gives you 720. Now, the 720 is your MAPE, right? MPE, right? You take a percentage error each time. So 25 divided by 75 gives you, MPE is a signed error. So minus 25 divided by 75 gives you minus 33, right? Okay, minus 33%. Minus 18 divided by 72 gives you minus 25%. Plus 45 minus, plus 45 divided by actuals of 125 gives you 36%. Okay, so basically the comparison is between, let me just change the ink color here. Okay, so the comparison for this is signed error, right, divided by the actuals. Okay, MAPE is just take the absolute value of this number, right? Absolute value of this number. That gives you this column, MAPE. So what happens? Your forecast errors or model diagnostics, right, become a little bit different, right? So basically what you do, you just take the absolute value of minus 33 to 33%. So these are all positive numbers. So at the end of the day, what you have as forecast error, right, is mean squared error is just this number, 720, okay? MPE is this number, 0.26%. MAPE is the average of all absolute error percentages, 24.14%, right? So we got all these numbers. Now let's talk about root mean squared error. Root mean squared error is the square root of the mean squared error, which is 26.83. So think about this. The 26.83 is not a percentage. It's actually in units, right? It's in units. Okay? It's in units. So which means the 26.83 is comparable to the scale of this observation. So the average demand for the month is, average demand for this particular item is 89 units, 89.2. So you can relate to the average monthly demand, right? So you're saying the mean average error for this product, model error, is 30%, right? Is 30%. So that's what you're talking about. Okay, so basically 30% is just nothing but basically taking the root mean squared error and dividing by the average demand. So so we just say the average error or the average root mean squared error is about 27 units, which is about 30% of the monthly demand. Now this number is not reported by APO anywhere. I just gave it to you for intuition, right? APO only reports this 26.83. right? So if you have a product that sells thousands and thousands, the root mean squared error would also be in thousands, right? So, that's something to keep in mind. But really, this is the most useful measure, right? Because this actually is a weighted measure. Now, I think it'll be good if APO says, okay, well, I'm also going to kind of do a MAPE on a weighted basis, but, it's not using a weighted MAPE, okay? So basically, with that, let's talk about the diagnostic here. So APO model error metrics are the diagnostics for each forecast model tested by the planner. These diagnostic measures help the planner review the quality of the models and improve them, right? So how do you do that? You can actually set forecasting alerts. The model errors can be used to set forecasting alerts to be triggered. So if you set alerts, right, then the alert will be triggered every time a model reports an error higher than the alert threshold, right? Now think about this. This is useful because at the end of the month, after you've done modeling, at the end of the month, when new history rolls over, it goes through the monthly cycle. The monthly job reproduces the model, right? It reruns the model. Then you may have new errors calculated. So if your errors now trigger the alert, then automatically you will get an exception report saying, of the 1,000 SKUs you have, about 200 SKUs are triggering this alert. I want you to look at them. Powerful function, right? So if you set the alerts correctly, then you can go back and look at those important SKUs and go from there. Now, this also has to be done in a good way, in the sense, in a scientific way, and also understand alerts from a business perspective, what the business requires. And thirdly, also keeping in mind the shortcomings of APO. Because if you don't understand the third piece, we have seen, like in one particular client, they had about 400 SKUs, but on a monthly basis, they got about 9,000 odd alerts, forecast alerts. So basically, after some time, this is what they told us during the diagnostic, that they are not using alerts and they have turned them off because it's just too much and too much garbage coming out of the reports, right? So they don't want to use the alert function. Obviously, because they have not set up the alerts correctly. So we went in and redefined the alerts, and the alerts went down to about like 40 alerts or so per month. So it depends on how you use this, leverage this function, because if first of all, the business requirement is important, right? What is important to the business from a modeler's perspective? And secondly, what are the challenges within APO itself that can cause alerts to be meaningless, right? So at this point, I also want to stop and ask you if you have any questions, right? So I think I addressed the last one. If MAPE is the most widely accepted form of error or accuracy, why is it not available in APO instead of MAD? Very good question. MAPE is available, but the volume-weighted MAPE is not available. And I have made many attempts to reach product development guys in SAP. If you're a member of LinkedIn, you may want to just check out our discussion between myself and one of the product managers in SAP. And it got pretty heated actually at one point in time because, although, he didn't really kind of understand where I was coming from, at the end of the day, he said that's not the priority to change it at this point because it's something that they will be looking into, but there is no guarantee that it will be changed. And as far as I know, I don't think these alerts, the MAPE, volume-weighted MAPE is actually in the works even for version 7. Actually version 7, I know for a fact that the volume-weighted MAPE is not there. It's still a MAPE, right? But I would say, hey, given all this stuff, given SAP has its own difficulties and the vast number of customers and vast number of products it has to support, I don't really know when would it be in the product fix cycle to get to this. But in the meantime, I would say, we just intelligently leverage the functionality that's available and create things around it, right? So, but anyway, I want to still kind of ask if you have any questions so far. Any specific questions, anybody? Okay, yeah, we are going to talk about it. We are going to talk about, that's a good question. I appreciate that question. The question is, how can I simply apply the root mean squared error to improve forecast accuracy? Very, very good question. And if I were a planner, that's what I would do. And that's what we have preached to the clients as well. And we will talk about how to use root mean squared error and how we can leverage the other functionality that's available to improve forecast. So, I mean, I think the point is just like, really stop complaining and just really get on with the program and see what we can do intelligently to do it better than the others who don't really understand the tool or who don't have the benefit of this training, right? Which is, they probably are still struggling with 10,000 alerts. But on the other hand, if we can use this meaningfully with a combination of the alerts and the combination of forecast comparison reports, then, we would have done a much better job and really would truly be in the path of exception management. Okay. So, so let's talk about the second piece here. So one is forecast alerts. Second is forecast comparison reports. Really powerful functionalities here, right? We want to use them in a combination. Now, I have to tell you, the forecasting alerts are there in other tools as well, right? And I think those are very, I've seen Managistics, I2. Managistics particularly is very user-friendly and also provides very intuitive alerts that you can set up, right? And you can set up alerts, with a lot of flexibility in Managistics. And it will also produce for each alert what type of SKUs it has and what can be done, that type of stuff, right? So it's very good. SAP can be leveraged to do that, something similar. Now, in terms of flexibility, obviously we are limited to what we can in the forecasting alerts. But I really see the forecast comparison is actually a powerful functionality in APO, that I think the other tools would be better off just copying this functionality, right? So the forecast comparison, what it does is it keeps a history of your forecast modeling process. Let's say you have the last 20 models. You worked over the last 2 hours, like drinking a lot of coffee and scratching your head and trying to come up with various models, right? You look at the textbook and you go back and APO manuals and you do a lot of models, right? And then finally you are like really helpless. Then APO gives you an option to go back and look at what you did the last 2 hours, right? You open up a report. It just shows you the models you used, the last 20 models you used, and what is the different error diagnostics that came out as a result of those 20 models. So you look through that and then say, wow, the 7th model you used was very good compared to all of the others that I've been struggling with. So you go back and say, I want to use the 7th model. You pick the 7th model and use it as your model, right? So which I think is a very useful functionality. Okay. So forecast comparison is useful to evaluate alternate forecasting models based on the diagnostic error measure, right? So I would say look at the individual diagnostic MAPE and MPE at the SKU level, and then also look at set the alerts and look at forecast comparison. Alerts are useful on a month-to-month forecasting cycle. Forecast comparison is useful when you're modeling a SKU at a particular point in time. Okay, so let's talk about alerts. So let's start again with forecast alerts. And so basically, as we mentioned before, okay, so I assume you all can see the screen and be heard. Okay, so basically, we'll talk about forecasting alerts, and as we mentioned before, there are 4 alerts available. We'll be talking about univariate forecast alerts in here. Okay, defining univariate forecast alerts. Alerts are defined in the master forecast profile settings, basically. Okay. Now, it would be good if if any of you could share with me, your experience. Have you used any alerts before in APO specifically? I know there are some users, some consultants here. Any one of you having used forecasting alerts before? The group from Hitachi, have you guys, have you done work in APO BP?
Yeah, we've used alerts.
Dave, Dave,
things
where
that
did
we
you
end
speak?
up using alerts for is, just more simple things like the status has changed or something along that line.
What has changed? I'm sorry?
It's like some sort of status code has changed or
Okay.
something along that line.
Message alerts, okay.
Really what you pointed out before, clients tend to have a lot of problems, and SAP likes to really push alerts as a vital functionality, but clients often have times that they put everything out there, and they end up with, as you were saying, hundreds or thousands of alerts, and then they end up turning it off. It's really hard for a client a lot of times to define what's the key thing that they want to test and have, run an alert on. And then the other side of it is that, of course, you have to write a mathematical model to be able to measure it and to have some sort of output, which can be difficult too if there's a lot of conditions or whatever else that they, sometimes I want it like this, but other times not, type things. So.
Right, yeah. So you've used actually for the other type of alerts, the message alerts and things like that.
Exactly.
Okay, very good. Excellent. Thanks, Dave. Michelle, did you have anything? I know you were trying to speak also.
Oh, no, it's okay, Mark.
Okay.
Yeah,
All right.
same thing.
Very good. Thank you. And, and I think I have also gotten some other responses, privately. Yeah. So basically, I think, so a lot of the experience has been something that I have shared with you before, that since the clients got too many alerts, the users got too many alerts, that at the end of the day, the IT group actually turns the alerts off, right? So that's so anyway, I mean, I think this can be used and this can be used very productively. So alerts are defined in the master forecast profile settings, right? So this is really not navigation training, but I'll just basically show you. So basically you go into the DP forecast profile settings. It's defined as where you maintain the forecast profile, and that's where you pick the univariate profile and then set the alert. And the alert is set up as a diagnosis group, right? So you may want to set up like diagnosis groups. You could have multiple diagnosis groups, and all of these diagnosis groups would actually produce the alerts. And then you have to associate the diagnosis group with the specific model in your modeling screen, right? So that you would do as a planner, right? Now here also there is some security obstacles that could come in the way because, sometimes you may not be able to choose or define your forecast profiles. There may be a master user or an IT business analyst who is allowed to do it. So which means your hands are tied, right? So you have to work with that person and you have to do a change request, and the change request has to go to India, and we have to wait for the Indians to wake up the following day, that type of stuff. And then that may go through a change committee. So it may just take a whole bunch of bureaucratic, hurdles before you come in, to say, hey, I want to use it in a productive fashion. So I think there are lots of challenges, but, some of these could be overcome with the periodic meetings that you have with IT. And some of this actually purely with with training, better education of both IT staff as well as planners, so that some of these things, because the boundary kind of blurs between the business and the IT when it comes to how you manage these things. And ideally, it will be better if you have a super user in the business who has access to these alert settings. And I have seen that as a best practice with some of the companies that we work with, which ideally is awesome because, you have a problem, you go to the super user who actually is either a demand planner or a demand planning manager who interfaces with the IT group and who basically asks them questions about what is being done, what are the things on their plate, that type of stuff. And so this guy has access to a lot of these things, and he would really appreciate the need for some of these things from a business perspective. So I think that is actually like, a very, very good practice if companies can follow that type of a model where, they talk to the users, and then, there is a super user that actually periodically or very frequently interacts with the demand modelers, right? So basically, you would use a diagnosis group to create, or change an alert definition, and that's where you would create the alerts, right? So let's just look at a sample univariate forecast alert, right? So let's just talk about the meaning of the forecast alerts first. Univariate alerts can be set as a trigger if an error exceeds the alert threshold. So what you need is what is called as an alert threshold first, right? You need the alert threshold. You need to say, hey, if the MAPE jumps over 25%, tell me, right? So you could say, well, my alert could be a combination alert, a MAPE greater than 35% and MPE greater than 25%. If both conditions are met, I want to know which SKU it is that the model has produced such a type of a result, right? If both conditions are used in the alert, the above set will capture those SKUs where the model is under forecasting the history, right? So you obviously know this, right? MAPE is 35%, which is pretty significant error of some size, whereas the MPE is constantly higher than 25%, right? So think about this. MPE is computed using actuals minus forecast. So if MPE is positive, that means there is an under forecasting bias. Forecasting is always below the actuals, right? So that would give you, an under forecasting alert, right? So consistently you have 25%. So at the end of the day, this is actually giving you an alert, right, for under forecasting. You can capture under forecasting. So basically, I think, the way you develop, you may have seen a screen something like this, the blue screen, into the profile screen. You basically create an alert group, and the alert group says, this is the diagnosis group that I am creating, and that is where I am defining a low bias alert, right? And the alert is defined as, MAPE is a threshold of 35% is set, right? And remember, this is actually in percentages. So you enter a number, and the number is converted to a percentage, right? And so this one is just a MAPE alert. So this is actually going to flag, the diagnosis group is a MAPE alert, and this is going to flag all of the SKUs that have a MAPE of above 35%. So I hope some of you are familiar with this SAP screen, right? This is actually where you go in and set your profile, and the profile is under the environment variables, right? So basically, like, this is just like, this will capture all of the SKUs that have above 35%, right? And the previous one will capture all of the SKUs that have 35% and 25% MPE combination alert, right? Now, if you carefully look at this, I think there are different things, right? If you carefully look at these screenshots, basically, look here, the forecast errors that will be reported that I set for all the SKUs under this profile, actually for my univariate profile, is going to be, I only want them to report root mean square error, MAPE, and MPE. I have ignored the other. It's like, information that I don't really need, MAD, MSC, or error total. I just said capture all these three and I'm good, okay? So basically, at the end of the day, the low bias alert, we created a different diagnosis group, and the diagnosis group actually said, MAPE is 35%, MPE is 25%. So anything above this, flag me, tell me, right? So, and then, obviously, it is going to report these in my error screen. It's going to report all of these numbers. But these are the ones that is going to trigger and give me an alert, so I can go in and take a look at them, right? In the modeling screen itself, there would be kind of a, an alert. There will be a symbol that will show up saying that, hey, this particular SKU has triggered an alert, right? So you want to be looking at this, okay? So, okay. So now, basically, so low bias to flag under forecasting, right? So if you look at actually what's happening here, this particular scenario is resulting in an MPE of 26%, MAPE of 41%. Okay. Now, if you calculate the tracking signal using the normal methodology, the tracking signal is 3.8764, and tracking signal above 3.75 means there is a persistent bias, right? Means there is a persistent bias. So in some sense, the tracking signal is calculated as a ratio of these two. There is a scale between these two, and that's how tracking signal is defined, right? So if you take this example, right, you just look at the forecast versus actuals. Actuals are consistently higher in 4 out of the 5 months, right? Only in 1 month you have the actuals coming in below the forecast. Every other month actual is higher than the forecast. So tracking signal is 3.8764, which we will explain towards the end of the presentation what it means. I put it at the end of the presentation because there is really no visible way for you to calculate tracking signal in the user interface, right? But the alternative is to look at a combination of MPE and MAPE and leverage and address your forecasting bias. Okay. All right. Let's see if there's any there. Okay. All right. So now there was another question that was like, can you set alerts for multiple SKUs at once? Yes. Alerts are set for multiple SKUs, right? You just generally define an alert, and the alert will flag, which SKUs that you have, you have issues. It'll flag those SKUs, right? You can define the alerts for everything, and then it'll just define, it'll pick those SKUs that have triggered the alert, right? So, yeah. Okay. All right. So let's move on here. So basically, like, alerts are powerful. But the one thing that I want to, I don't think we addressed that here. Okay. So let me just illustrate this real quick, and then we'll go from there, right? So let's say, this is a SKU. It's actually we have a model that we use for our own, which is kind of a made-up bakery that uses pastries and cakes and all that stuff. And that's our sample configuration model, just a standard template. So with a very short history, but with an explosive trend, right? It has 7 months of history, growing volume. So, we'll do that. We just use the model, pick the linear linear regression model. And for some of you model gurus, I think it's model strategy 35. Accept all the parameters, run the model, open the forecast errors tab, strip, and interpret the results, right? This is like, this is an exercise that we use in class on the on-site training, right? So if you look at this, right, forecast and actuals for 1006, right? So this is pretty good, right? I mean, it's really short volume to do a whole bunch of robustness here, but still a linear model seems like would work pretty well, at least in the short run, that the trend is going up. The only thing is, obviously it looks like this point is a little bit of an outlier, right? It just like jumped from 12,000 to like 15,000, 16,000 units or so. Okay. So we use a linear regression model that seemed like a pretty good model, and then we are just looking at the model errors for the linear model, right? So the model error, it said the MAPE is 20.25%, right? Think of these as percentages. Root mean square error is 1,800.22. The mean percent error is 8.85, but negative, right? I think it must be a German convention, so I don't really know German, so possibly Germans put the negative at the end. So it's negative 8.85%, right? So the mean percent error is 8.85% negative. So which means, what does it mean? The negative 8.85% means, does it mean under forecasting or over forecasting? Obviously, this is over forecasting, right? Yeah. Okay, good. So this is over forecasting. So the model has over forecasted the historical period, right? That's what this means, right? Negative 8.85%. So then I look at it and say, hey, maybe I just need to look at the outliers, make some adjustments and all that, right? And maybe I'll do that, right? Next, what I do is I just go in and say, but before that, let's look at the model error and exposed forecast, right? So the exposed forecast is right here, right? The exposed forecast is here. And then the corrected history is another key figure that's right here, right? So basically what it is doing is it is actually computing the forecast error as a result of these two, right? as a result is as comparing forecast versus the historical number, right? You may have defined these as different key figures, right? So this is how you have defined this, right? So this is the difference between the two. That's your model forecast error, okay? Now, go back to, now here, think about this. The corrected history is a number that SAP inserts based on outlier corrections, right? If it thinks the outliers are there, it corrects them and comes up with a new history for your modeling purpose. And the interesting thing is it calculates your forecast errors or exposed forecast errors based on the corrected history, right? The outlier adjusted history. So basically, model diagnostic may cause you to change the model parameters, right? You keep the same model, but make adjustments to model parameters. So once you say, hey, listen, I think the MAPE is a little too high in that case, I'm going to go back and change the model, right? I can change the model, and I can change alphas and betas in the screen manually because I think I can do a little bit better once I know the starting point. I can also look at the outlier screening intensity, right? Maybe it is picking out too many outliers, or maybe it's not picking any outliers. I can do a variety of other things, right? Shift adjustment, stuff which we don't cover in this course. So, there are different ways that I can do. Now, if I just say outlier is a problem, and I just use an outlier threshold, right? Outliers to flag out. So I change outlier setting, right? I can change outlier setting now. Let's say I change the outlier setting to 1.25. It's a threshold, let's say. So when I correct outlier threshold, now for the purpose of this course, just think about this. A number that is as low as 1.25 or below, right, means it's a very tough screen for it's a very liberal screen for outliers in the sense it will throw away a lot of observations as outliers. A number that is greater than 2.25 or 2.5 will not pick as many outliers. It would just pick only one or two, maybe none, basically. So, and then you have the liberty to change the outlier threshold. And there are a lot of challenges with this also, okay? So the interesting thing is, if you set a low outlier threshold, what will happen is it will correct the outliers, right, and report a new error. Now, the MAPE has come down to 10.25. After outlier correction, the MAPE has come down, right? But then the interesting thing is, the one thing that you want to think about is, the forecast has not really changed. It actually has changed the historical periods, right? It has changed the historical periods. So changing the historical periods, now the true adjustment has been here, right? Obviously this one, it actually increased the history, came up with the right forecast. But all of these numbers, right, this number, it has just dropped the number to this, right? So not because the forecast has changed. Now, with the corrected outliers, it is now using the corrected history to come up with the new forecast, right? Which is actually good because, you are throwing out an incorrect observation, coming up with the right forecast. If it increases the model quality, that's a good thing. But on the other hand, if it increases the MAPE without, if it lowers the error without increasing the model quality, then that's not a good thing because if you set a low outlier threshold, it can throw too many points out and invariably end up with a model that's too simplistic, right? It's an easy way out for the modeling engine to escape the rigors of the model requirement. So the only caution, this is like I'm mentioning outlier corrections, is because the one catch here, one challenge here is setting a low outlier threshold can spuriously result in forecast errors that look deceptively low, right? So in this case, because it's not comparing with the original history, it's comparing with its own outlier corrected history. And the interesting thing is the outlier corrected history is really something that is a derivation of the forecast model that you use, right? So which means it's almost like begging the question. You thought an observation was outlier, and you went to your forecast model, and then you picked that forecast number and put it as a replacement for your outlier, and you reforecasted it. Obviously, your errors are going to be lower, right? Because you just threw away points that you thought were not really were really, you threw away points that were difficult to forecast, right? So this is where this is just a line of caution, right? Because you can always lower the outliers, and then you can come up with error screens that look very nice, right? But the model may not be a good model. The model may be useless, right? because it reported very good fit and very good fit, but then the model is not as good. So the outliers, you have to be very careful with using outlier thresholds and outlier corrections because you want to see how many observations are thrown out as outliers, right, in terms of the modeling. Okay. So basically, right now, I have to say that the error reduction that happened here, right, now the MAPE went from 21% or 20% to 10%. The 10% reduction, only part of it was caused by a legitimate outlier correction. The rest of it was caused by the outlier corrected history actually chasing the forecast model. Points were thrown out, right? So basically, I think that's the impact of outliers that I would address as a caution, right? Now, we'll talk about tracking signals before we talk about the forecast comparison reports, right? Tracking signal measures the persistence of errors in one direction, right? So it's a robust measure of forecast bias, right? And the threshold for tracking signal is 3.75. If the tracking signal exceeds 3.75, this indicates persistent bias that needs to be addressed, right? So, so if you have a higher TS, then this means the bias could have come from either level or trend that is not recognized by the model, right? How many of you are already familiar with tracking signal? Some of you may have taken APIX courses, so maybe you probably have some idea about tracking signal. Maybe some of you do. So basically, tracking signal is nothing but sum of the signed errors divided by the average of the absolute errors. So what happens, it's almost like a comparison of MPE to MAPE, right? MPE to MAPE, right? Slightly different because remember the MAPE as used in APO is a percentage error, the average of the percentages. But here it's the average of the absolute errors, right? So at the end of the day, it is something close to looking at the signed errors divided by the mean absolute deviation. The idea is if the numerator, if there is no bias in the forecast, the pluses and positives would invariably wash out and the number would be 0 or something close to 0. But then the absolute deviation would not wash out. The pluses and minuses would all add up, right? So it's really saying, hey, my persistence, how much does it compare to my total absolute deviation? That's the comparison of tracking signal, right? So let's say if it is pluses and minuses, let's say you over forecast 1 month by 10% positive, then next month 10% negative, next month 10% positive, next month 10% negative, right? In that case, it's all washed out. So if you're in an odd month, right, the following month you have a 10% positive. So if you just take an average, then you would come up with a plus 2%, let's say, over 5 months, right? Because 10%, everything washes out. You have a total is 10% divided by 5 is plus 2%. So which means it's a very small number. It's oscillating, very small number, so you don't really have a bias. But if it is all in one direction over the long period of time, then obviously this number would be higher, right? If all of your error, if you have over forecasted every month, right, then obviously your total error would be, comparable to your mean absolute deviation, right? Would be comparable to your mean absolute, your total error would be comparable to mean absolute deviation. So in that case, when you're summing them up, it would be a multiple of mean absolute deviation. So that's how the threshold of 3.75 is calculated, right? So if it is higher than 3.75, then obviously you say it's under forecasted. If it's lower than minus 3.75, you say it's over forecasted. So in this particular case, a quick example where your tracking signal, you can calculate this for each month, right? Tracking signal ends up as 0.06, right? For the 5th month, it's 0.06 because we said it's the sum of the sign deviations. Sum of the sign deviations is 1, right? Divided by the average of the absolute deviation is 18, right? So the tracking signal is less than 1%. It's 1 over 18, right? It's a sum of the sign deviations, right? If you go back to the formula again, sum of the sign deviations divided by the mean absolute deviation. So the mean absolute deviation is 18. 1 over 18 is less than 1%. It's actually close to 1%. 1 over 18, right? So, is about 1%. Okay. So on the other hand, let's say you have, the similar example like what we had in the low bias alert, right? The same example that we had before. So you have, you calculate all of this stuff, right? And in this particular case, right, the sum of the deviations is 138, right? The average absolute deviation is 36. Mean absolute deviation is 36. So your tracking signal is this, right? 138 divided by 36 gives you 138 divided by 38 gives you 3.876. That's your tracking signal. Now think about this. It is greater than 3.75, so is there an over forecasting or under forecasting bias? What kind of bias here? Under forecasting bias, right? This is the under forecasting bias. Okay. So now under forecasting can also be caught using this MPE and MAPE. Look at this. The MPE is 26%, MAPE is 41%, right? 26% and 41%, and that results in an under forecasting bias, right? Because this number is positive, right? So positive means under forecasting. So you have a 26 and a 41%. Now there is a formula that you can write with MPE and MAD, and that's what you probably would be using in your in your backend programming if you want to come up with the tracking signal, right? So for our purposes, right, the alert report that I gave you, the under forecasting low bias report that I showed you, right, that should, if you define something as your threshold is 25% MPE and 35% MAPE, then that would capture the low bias, and that's how we came up with that number, right? So we recommend the 25 and 35 and say, hey, if you guys flag this, then that means it's an under forecasting error, okay? All right. Okay, so we'll go to the forecast comparison technique in a minute, but I want to just really open it up for questions here, and I also want to ask you a question. Okay. Here is the question for you, right? So now I told you that you could have an alert, under forecasting alert could be set up for 26% by using MPE threshold of 26%, MAPE threshold of 41%. Now, I would like to ask you, how would you set up an over forecasting bias alert, right? Over forecasting bias alert. You can either speak up. You've been awfully quiet, so you either speak up or you can actually just type in your answers. So I'll give you a couple minutes here. Just based on theory that we talked about today, right? How would you set up an over forecasting, an alert for over forecasting bias? Anybody? Okay. Correct. So basically, you would define the MPE to be a negative number, right? So MPE would be a negative threshold is what would trigger an over forecasting bias alert. So good response, right? It'll be a negative bias number. So here's the trick question. So what would you enter in the APO interface?
Can you say that again, Mark?
Okay, what would you enter in the APO interface for MPE? So if you just go back here, let me just go back to that screen here. Okay, so in this screen, what would you enter here for, what would you enter here? Right here, obviously, you want to enter 35%, right? Right, so you would enter 26, right? 26 minus, correct? Right, but not here in the profile. You would enter 26. So here is the challenge that we have had, right? The very odd thing is APO does not accept a negative number in the thresholds. So now that Steve is actually typing in 26 minus, I have never done that. So maybe I should try that. Maybe I should try 26 minus and then see if that works. Because we have tried minus 26 and it actually wanted a positive number. So basically to answer the question, so you would type in 25, right? 25 or 26, whatever is your threshold, and then you would type in 35 here, right? That would give you the alert threshold for a high forecast bias. Okay, that'll set up a threshold for the high forecast bias. So, I mean, we have had this issue, and we have taken up with the SAP, and it's also there as a note and things like that too. So, I mean, as far as I know, it doesn't allow you to flag over forecasting. It allows you to flag under forecasting. But now that Steve mentions 26 with the minus at the end, I'm like thinking, oh my God, I should run and try that now. So maybe that'll work. So, so basically the response is right. So which means MPE should be a negative threshold for flagging over forecasting bias. Very good. Thank you. All right. So let's go back to okay. So we talked about all this stuff, and then we'll talk about revising the forecast. These are the principles that you would follow in terms of revising the forecast, right? If error is too high, you must look for ways to improve the forecast by finding a different model. Okay? Look at the fit graphically and see if your model is not capturing demand components correctly, right? So error is too high, you go back and look at it graphically. Now this has been another challenge that I mentioned, right? So currently, I assume that you have used the graphical interface, right? So, and if your model is not capturing demand components correctly, so you would automatically see it. If seasonality and trend are not being captured, then you have to question why, using the graphical interface, right? Now, this is where you would find that, if you had let APO pick the model automatically, it may have used a very weak outlier threshold and had thrown out a lot of seasonal observations, and then it did not fit the right seasonal model, right? That's one possibility. So try alternate models and compare model quality. A handy tool is to use the forecast comparison report in univariate forecasting, right? So let's go and look at forecast comparison technique, right? So forecast comparison technique is a report that's being used, right, that would compare different models. So let me ask you, how many of you are currently using or have you seen this forecast comparison report? You can chat privately and tell me, just I wanted to kind of get an overview. How many of you have seen this forecast comparison report, used or seen it at all in your APO? I mean, it's a very powerful tool, and it's a tragedy if the IT department has not turned it on for users to use it. Okay. All right. So basically, I mean, I think so. Let's see. So one of the things, this is probably a homework that you have to turn in. You don't have to turn in. You may want to go back to your IT departments and ask them for the forecast comparison report, right? So, if they want to start a change request, they should probably start that as soon as possible, right? Okay. So basically, the forecast comparison report gives you a comparison of all the models. And I have to tell you, this is a great tool, and you don't want to underestimate the power of this tool. This is a very good tool, a very useful tool. So when you look at the forecast comparison report, and I'm just saying, for my product, what have you, right? And my product EM1003A and all that, and it's a candy company, and I just looked at all of this stuff, and I have different forecast versions. I can also sort this, like the last 20 models. Obviously it's a screenshot. I can't just take the elevator down or up. So I just go in and say, I have all these things available, right? I have a MAPE, MSC, root mean square error, MPE, MAD, all of these things available. I can even sort by R squared if I want, right? You don't want to do that. So let's say all of these sorts available, and remember I told you the root mean squared error is a weighted measure, and it's a very powerful measure, right? It's a very powerful measure, right? So now, if you take the root mean squared error, right, I know it's a weighted measure. The only challenge is it's not a percentage, right? So I just go in and click on the sort, root mean squared error, right? It automatically sorts it from the lowest to the highest, and then tells me, model 11 is a very good model. Your root mean square error is the lowest, right? 1,562.09, right? Now, and then I also look at the MAPE. The MAPE is also low, 15.29, right? I look at the MAD. MAD is also low. But, these may not always be agreeing. They may be different for different SKUs. In this case, they agreed, right? Now, here is the thing about APO. Now, APO, the product designers, use the right math here, right logic here, and they use the absolute value threshold here, right? They just put MPE threshold here, right? So they report that as, you see the absolute sign here, and they show it, so they rank it correctly, whether it's negative or positive, they rank it this way, right? But then we have the problem in the alert screen, you cannot enter a negative or a positive number, right? So they understand here that it could be negative or positive. So when they sort it, you could have a problem if you sort it by negative and positive, because negatives will always show up first, and that will not be an issue. That will be an issue, right? So for those of you who understand the math here, right, the algebra and the math here, if you don't have the absolute sign, a number that has a very high, over forecasting bias would be rated as the number one model, right? Because if you have a minus 75%, right, and a plus 75%, and then you have variety of forecasts in between with a 0% in the middle, right, the minus 75% model would show up on top, which is not a good outcome, right, because that model is not a good model. It's extremely over forecasting, right? We don't want that to be sorted. So what they did was they used the absolute value sign of the MPE. So they picked the model that's closest to 0, right, if you are using MPE as your threshold, right, for your bias. So regardless, anyway, so we use the root mean squared error, and it said, 1,562 is, is the root mean squared error. That's the lowest model. That's the best model here, 15.29, and you say, I want to use this. I want to use this model. Whatever was my 11th model, that's what I want to use. And this is the maximum number of forecasts I can have the comparison report take, look at, which is 30, right? I can look at the last 30 forecasts. So now I just go into the parameter screen, right? Previously, I am in the forecast error screen. I rank it. And then I know 11, 10, 13, and 12 are the best. Then I just click on the parameter screen, right? And then I go to the parameter screen, and then it tells me, okay, model 11 is a linear model, model strategy 35, right? And it also gives you some of the parameters used and things like that as well, okay? It just tells you what's the alpha, beta, gamma, R, delta, epsilon, all this other stuff. So, don't ask me what these are. That's actually going into the modeling part of the seminar, right? Not the seminar, but. So anyway, so forecast version is 11. Strategy is 35, which is the linear regression model. And, so basically it says, go back to 11. If you go back to 11 and use a linear regression model, boom, you will have the lowest 15% MAPE that you liked so much, right? You can use that. Okay. So this is how you actually use the model comparison, the forecast comparison report. And it's a very useful tool because you can actually just keep an audit trail of what you did, and you can also go back and take a look at what you liked the most, and then you can use it. Obviously, if you model a lot, it's going to change. It's only going to keep the last 30 models in its repository. Okay. So basically, I think that really brings us to the end of the seminar on the demand metrics in APO. So basically, what kind of a learning summary here. Learned about model diagnostics. How do we use in sample or exposed forecast errors to do model diagnostics? And we also looked at the definition of MPE, MAPE, and root mean squared error in APO-DP, right? And we also said the other measures are not as useful as these three measures, right? The ones that you can ignore right away are the error total and the mean squared error, right? The mean squared error is actually the most meaningless, right, to look at. The MAD is useful in certain cases, right? So, but really these three are what you want to work with, right? MP and MAPE make sense from a relative perspective because they are percentage numbers. Root mean square error, on the other hand, is a number that uses, root mean square error will give you the, the weighted calculation. So it's comparable to the weighted absolute percent error that we used before. And then finally, we talked about the robustness of the error measures when outlier adjustment is used. So I would like you to caution when you're using outliers, because adjusting outliers would be kind of self-fulfilling prophecy, because if you adjust the outliers, you can artificially create an error metric that actually says the model quality is very good, in a spurious way, right? So you want to really question outlier adjustments. Outliers can be used for genuine outliers, right? But, really, you want to think about if the errors change dramatically, then is the outlier causing the problem, right? If the outlier is adjusting the actuals, so that the model is a better model, then that's good. But if the outlier is adjusting the actuals without really changing anything to the model, then it's not improving the model, but it's just improving your reported error measure, right? Which is kind of really not a good thing to do. So we talked about the APO-DP illustrations, and we also talked about learning, tracking signal, and we said, tracking signal is a combination of basically MPE and mean absolute deviation, right? It's a combination of MPE and MAD measures. And that's the reason why we said we will look at MAD also, because MAD is going into the tracking signal. So basically, at the end of the day, use tracking signal and use different model diagnostics and adjust the model parameters in the model itself. So once you understand the diagnostics, then what you do is you go in and either adjust the model parameters, which means let's say you pick the Holt-Winters model, right? The Holt-Winters model, I think it's like strategy 56 or so, right? So you pick the Holt-Winters model, and then the Holt-Winters model results in a trend seasonal. So basically you're using alpha, beta, and gamma, right? So you like the model, but your diagnostic is not good. You can actually adjust the parameters first. But if you don't think that is improving anything, then you can just say, I'm going to throw away Holt-Winters. I'm going to go to linear models, right, with the trend and seasonality. So I'm going to go to model number 94, right, which actually is going to give you a linear model, right, because I am throwing away the model itself. I don't like Holt-Winters. I don't like exponential smoothing. I'm going to go to deterministic time series regression models, right, which is, remember, that's one of the models that we showed early on in our seminar. So finally, we talked about alerts and, setting alert thresholds in your forecast profile, in the univariate forecast profile. And then we ended the seminar with interpreting the forecast comparison report, right? And I said this is a very useful tool, very powerful tool, and you definitely want to have this in your toolkit. So, I can give you a summary today in terms of what I have heard, right? The companies that attended today also have not seen the forecast comparison report or have used the forecast comparison report. So I think I would highly recommend that, you may want to go back and chat with your IT and say, hey, how we can bring this live and use it, okay? I think the consultants, I think, that are in the call, I think one of them has replied that they have seen it. So, so basically, I think that's the seminar we have today. And I will go through and see if there are any questions so far that I have not answered. At the same time, would you also please, raise your hand, speak up if you have any questions, because we still have we have another 10 minutes or so. Let's see. Okay, one of the questions was, in APO, how do the alpha, beta, and gamma parameters compare to the components of ARIMA? Now, I can generally tell you that the alpha, beta, and gamma in exponential smoothing compare to the moving average component of the ARIMA models in the general world, right? And in APO, the alpha, beta, and gamma are modeled for coming up with an exponential smoothing forecast, exponentially smoothed forecast. And there is no ARIMA in APO. But generally what's happening within APO is the alpha, beta, and gamma, you can either manually set, or you can also have the system optimize and pick the alpha, beta, and gamma for you. So these are like the different strategies that you have to pick. Okay. Another question was, okay, I think we have answered the question on MAPE. Okay, we also answered the question on RMSE. So let me ask that question back. And there is a question on how can I simply apply the root mean squared error to improve the forecast accuracy. So did we answer that question? Root mean squared error is a weighted error. And the best way to use that is to look at the forecast comparison report after you've done a few models. Because, this is an absolute number, unless you remember the previous models and what they gave you, or use like a cheat sheet that and you note down what are the different RMSEs for the model iterations to see if it's going down or not. I mean, I think since it's a number, you can actually probably just remember for that one skew. But rigorously, it'll be good if we can go back and look at the forecast comparison report and use the, and then look at the root mean squared error. Okay. I think I have covered a lot of questions there. Okay, I think I have some more questions here. Oh, okay. So here is the question. What happens if the comparison tool is not being used? Is the RMSE useful in any other way? That's a good question. I would say that you ask, you basically look at MAPE, as kind of an approximate guide, right? And then use the root mean, and then also take a look at the root mean squared error, right? So the comparison report gives it to you in one screen, the compilation of RMSEs, right? It is the same as you are like writing it down in a cheat sheet, right? Like on a sticky note, when you're modeling. And you can just write down the RMSEs and then say if it is generally going down or not, right? From one forecast to the other, right? So that's exactly. So you would look at it graphically and you will also look at it, in a comparative fashion. The forecast comparison report allows you to take a look at it once you've done the modeling. You go back and take a look at the forecast comparison report screen. And obviously, you can also open 2 sessions. And so it's kind of a nice to take a look at, right? So regardless, I would say root mean squared error is very useful, right? So use the MAPE as a guideline. And then you just take a look at, let's say you come up with 2 or 3 models that you're pretty close. Then you eyeball the root mean squared errors, right? You are in one screen that says root mean squared error is like whatever, 45,000 or whatever. And then redo the model and it says root mean squared error is 38,000. Maybe the second model is better, right? So, it's just like any other number. You just have to remember. It's easier to remember a percentage because it's between 0 and 100. And root mean squared error is a number, right? It could be large for large SKUs, right? So, yeah. So it is root mean squared error is very useful. That I don't know. The other question is, can the root mean squared error be dynamically linked to inventory target setting in APO? That I'm not sure. That, I can find out. But, I don't really think so. Because the root mean squared error is actually set up in, it can be, programmatically it can be done. Because at the end of the day, you need to pass that back into your supply system, right, to use the root mean squared error. But the other thing is, and I'm not even sure if it would be that useful to dynamically link it. The reason being, you don't want the safety stock and inventory target setting to be like a yo-yo, because the root mean squared error number would change